The views expressed throughout this podcast are solely those of myself and the guest and do not necessarily reflect the views and opinions of ATCC or any other institution. Hello, and welcome to Behind the Biology, brought to you by ATCC. I'm your host, Dave Yarmush, and this is our first episode in our series with Nilay Chakraborty, the head of the Cryobiology Research and Development Department at ATCC. In this series, we're taking a different approach from our typical, and this episode will contain the principal focus on Nilay's personal journey, while the others will turn to the specific innovations of thaw-ready cells in the microquant system. For now, listen in as we explore his unique path from mechanical engineering to becoming a leading figure in cryobiology. Thanks for coming on the show, Nilay. Before I ask you more about your background, I'd like to start with the now. So, you are the head of ATCC's Cryobiology Research and Development Department. What does your group exactly research in cryobio?
It's an excellent question. Yes, I head the cryobiology group. It's within BioNexus Foundation of ATCC. And my group really looks at how we can create new technologies and find new avenues for ATCC materials to reach our customers' hands. That means innovative format, innovative product that involves ATCC's organisms as well as cells and cell lines. Right? I can go a little bit deeper into it if you like, David.
Yeah, that'd be great. So this is, by the way, all materials, like you were saying. It's not just specifically bacterial microorganisms or specifically human cells. It's everything in our catalog.
Everything in our catalog. So that was the interesting, challenging part for me, right? When a couple of years back, when the leadership from ATCC reached out to me, that was the challenge. That ATCC is almost like a 100-year-old organization with more than 80,000 products in the catalog. And the way we define the products where, well, I have this organism, we have that cell line, right? How do we, it was a more of an existential question that how do we survive, how ATCC would look like 100 years from now, right? Next 100 years.
Okay.
Right? So that got us started. Our focus is developing technologies and enabling technologies to create new generation of ATCC product. So that means format, that means delivery. Format and delivery are two most important things for next generation products, and we work on them.
Okay, so how does cryopreservation lead into a new generation of products?
Excellent question. So if you use the word cryopreservation in the broadest possible sense, it is a preservation technology, right? It is the same way how many of the food materials that we take in every day, right? Many drugs we take in every day, they need to be preserved in order for any biologically relevant material, be it bacteria, be it virus, and whatnot, right? Or cells can reach our customers. That link is enabled by biopreservation technology, essentially cryopreservation. So that's what our working space is. That's our working space.
That makes a lot of sense. Now, I do want to ask, because you specifically run the R&D portion of the cryobiology group, what about freezing things still requires research? I know, don't get me wrong, I understand there's more than a few ways to do that, right? There's the classic throw something in your freezer like everyone does at home with their foodstuffs. Freeze drying is an option, and that has a very interesting technology behind it. But as far as living tissues, microorganisms, what does it take, and what's still to learn?
Again, amazing question. I would say that we started out as a research and development unit, and we have expanded our capabilities, and now we are even enabling manufacturing. We took on a manufacturing portion as well, right? Specialized manufacturing based on uh, the technologies we develop. So products that are coming out of ATCC, um, we are also satisfying the manufacturing function to it, right? So R&D focus is still there. We have expanded that scope. Um, to go back to, but there is a very important component to your question where you essentially asked, what's special about freezing stuff, right?
Mm-hmm. Right.
Right? I mean, we do it every day, right? What's the problem there, right? So that is very simplistically to answer that question. We freeze because we want to preserve the bioactivity of a product, right? Product, I am using the word product in the broadest possible sense,
Right.
right? It can be protein, it can be DNA, it can be RNA, it can be a virus, it can be a bacteria, it can be a cell line, right? But when it comes to freezing part, why do we lower the temperature? We lower the temperature so that the materials, the bioactivity component is preserved. But the way the physics, biophysics part, or the way the preservation science works is that it is not that simple. You almost need different recipes for different types of product, right? That is the starting point for baking in convenience in a product. So yes, you are freezing products, but what if the process takes 5 days to complete? That's an opportunity for improvement, right?
Mm-hmm.
Or say you receive a cell line and it takes upwards of 2 weeks to culture it to the level that you want. That's another opportunity for improvement, not in the cell culture part, but maybe we can do something upstream and change things in the way we preserve things. So that's the opportunity in this space where we can bake in customer convenience, bake in relevance of the product, as well as we can standardize the product outputs. So three big things can be included in a product, and thereby we can increase the value of a product. We can save money, time, and effort.
So it's more complex than just dipping a vial into liquid nitrogen and shipping it out.
Yes, yes, I know it. I'll have to say that that has been the way. That's the most relatable way to a scientist or somebody who is working on the bench connect with preservation, right? You
Right.
put it in liquid nitrogen, that's it. And when you thaw, right? But that is that is the optics you get before somebody like engineers start getting involved into the field, right? We There is distinct opportunity to improve that experience of it.
Right. Because as you were saying, the different recipes for the different circumstances, that
Yes,
requires a lot of fine tuning. Now, I'm very glad that you mentioned or you referred to yourself as an engineer
yeah,
because from a fairly cursory search, your background doesn't scream cryobiology. It was biomedical and mechanical engineering, at least in name. Um,
yes.
so I've got a couple of questions related to that. But first, how did you find your way into what at least sounds like a very different field? I mean, I see the I see a link between cryopreservation, biopreservation, and biomedical engineering, but it doesn't seem like it's also a very direct path, if you understand what I'm saying.
Sure. No, it is not. And thank you for that question. Um, I I started out as a mechanical engineer, industrial engineer, and my area of focus was heat and mass transfer and essentially thermodynamics, if you want to say. And as I did my PhD was in mechanical engineering. Now, I have a business background. I have an MBA. And one of the things that we learn in business school is that, okay, if you have a tool, you need to use it to solve something unique and that is impactful. That
Mm-hmm.
thought process took me into the path of biopreservation or cryopreservation because it's a very complex process that has application of heat and mass transfer, thermodynamics, and all the engineering applications that you can think of, right? So same cryogenic concept, low temperature heat transfer concepts that are probably used to keep rocket engine cold, you know, can be applicable when you are trying to preserve something, right? It goes back to molecular mobility. So it's the unique ability to look at a problem from different optics, from the viewpoint of um, problem solving slash understanding the impact kind of optics, took me to the path of cryobiology, right? And yeah, I in the process I worked with some very big names in the field. I have been working on this strategic application of biopreservation as a field for upwards of 20 years, 25 years.
Wow. That makes a lot of sense when you lay it out that way. I am curious, and this might be a naive question, but it seems like, or it seems to me that the concepts of molecular mobility, thermodynamics seem, I don't want to say simpler, but maybe more intuitive in mechanical settings than in biological settings. So, assuming that's true, what were the challenges that you faced as you transitioned from the mechanical side to the biological side?
Another amazing question. So yes, I mentioned to you the unique looking glass that an applied field can bring into a basic science field, right?
Right.
So I think one of the biggest impact that I had was able to apply engineering and strategic management concepts to solve biological problems related to this field. Um, so, several different, couple of technologies that we were able to develop. If you come from the biology side, you will think about that's so out of the box, right? Why you are um, doing this to a cell because we don't do that. So that's the thinking outside the box kind of idea and applying the concepts, thermodynamic concepts of space and glass transition and all those concepts, if you can put in like a jigsaw puzzle,
Hmm.
the end result can be a very useful product. Fundamentally, it is the same cell or the bacteria that you are working with, but that meddling with the system can give you a product that saves time, that saves effort at end user level, that saves money, right? So all these things, it increases the acceptance. That's the fundamental, that's the secret sauce.
Yeah. So, how many of these applications are shaped towards the downstream usage? That is to say, if you have the expectation that a cell line, a bacterium, what have you, is going to be included in this assay versus that assay, do they need to be treated differently, or is it more related to the nature of the product itself?
It's a mix, right? But I would say the applied concept focuses on the entire band of usage of the product. And
Okay.
also, while developing a technology, we ask the question that rather than customizing the preservation process for, uh, say, bacillus as opposed to a uh, gram positive, gram negative molecules, can we find a platform technology, right? So it is easier on the processing side. So this goes back to the upstream and downstream effect of a technology. So we pay attention to both. It should be easy to manufacture. It should also be easy to use. Sounds very simple, but this laser focus on product and customer usage and acceptance is very important and transformational in this field.
Right, and delicate, I'm sure.
Yes,
So that puts a large degree of interest onto the generalizability of a method, right? You don't necessarily I'm sure in some cases you can't get away from having a specific method for different classes, so prokaryotes or like you said, gram negative versus gram positive, even um, eukaryotic cells probably even more different. But you are saying that exactly that the generalizability has such a high degree of value that it is worth going through the added layer of difficulties to achieve that.
absolutely. So this is where that looking glass, say the fundamental biophysical understanding and applied engineering looking glass is very helpful. To a molecule or a gram negative bacteria, they don't care. They're a gram negative bacteria, right? If there is a right condition, they are going to survive, right?
Yeah.
And it will help your assay, right? So from an applied point of view, we can look past that. These classifications are somewhat artificial. We can look at the thermodynamic makeup of the system, right? We can look at the molecular mobility and other things and make a decision based on that, right? So that's the paradigm shift in terms of looking at a problem and offering a solution, how it is. It is simple concept wise. It takes a lot of effort and grit to follow through it. And you see the example, we recently launched two products based on the platform technologies created at ATCC. One is at Acid Ready Cells, and another is MicroQuant portfolio. So
Yeah, that's great. And we'll be talking about those both more in the next two episodes. Before
sure.
I let you go, I am particularly curious. Are there any products or organism types or anything that just don't comply with the preservation techniques that have existed in the past or you've developed at ATCC? Anything that's a particular problem child?
We are actually working on a couple of different, very unique and exciting technologies. I cannot really
Yeah,
tell
I
you a whole
understand.
lot about them, but we have some very exciting technologies in store. And to answer your question directly, yes, like I said, biology doesn't care about our application, right?
Mm-hmm.
But if we understand biology at a different level, then we can offer a solution that is more convenient. That's the root of the entire field I'm working with.
Excellent. I think that's a great summary. So I appreciate this, and we'll talk soon about the thaw-ready cells.
Absolutely. Looking forward to it.
Likewise. Traditional training in mechanical engineering doesn't sound like it would foster the path that Nilay took into cryobiology, but the details betray the similarities and how that education benefits a surprisingly complex technology. His focus on customer needs over innovation for innovation's sake is deceptively unique in science, and I encourage you to stay tuned for our next episode, where we're going to get into the specifics of thaw-ready cells and what that means in the context of cryobiology.